Unlike optical remote sensing, passive microwave observations can measure both the leaf and the wood component of above-ground living biomass through a retrieved property termed the vegetation optical depth (VOD), by virtue of the sensitivity of passive microwave emissions to water in the environment. The VOD retrieval algorithms use a radiative transfer model to extract soil moisture and VOD. Essentially, the vegetation is considered to behave like a one-layered semi-transparent medium, and the VOD as a measure of the vegetation transmissivity with a negative exponential relationship represents the degree to which the vegetation attenuates microwave radiation emitted by the underlying soil and the vegetation itself. The VOD increases with vegetation density. Over dense vegetation, the transmissivity gets closer to zero and the microwave emissions are dominated by vegetation. The annual averages of VOD and NDVI during 1987 to 2006 were plotted against each other based on their land cover types. It can be said that the spatial distribution of VOD and NDVI is highly correlated over grassland and cropland. For forested regions, NDVI is likely to become saturated over dense canopies, whereas VOD may still record differences due to its deeper penetration. Over shrublands, the relationship between VOD and NDVI lies somewhere between grassland, cropland, and forest, likely related to the attributes of shrublands as a varying mixture of grass and wood component. Spatial maps of correlated coefficients between monthly value of VOD and NDVI show high correlation, like over Europe, Australia, Africa, indicating that VOD generally captures similar seasonal cycles as NDVI. Over tropical regions, the minimal annual variation of VOD leads to lower correlation with NDVI. Both annual changes in VOD and NDVI show similar trends and dissimilar or even opposite trends over different regions. For regions primarily represented by grassland and shrublands, the long-term changes in VOD agree well with precipitation, but the trend is sometimes different from that in NDVI. These discrepancies are most likely due to the different vegetation characteristics represented by VOD and NDVI. Thus, the VOD of grassland may decline in precipitation, but NDVI may remain unchanged as long as green canopy cover is maintained. The Southeast Amazon region is a known hotspot of large-scale deforestation, which is evident in the microwave-based VOD time series, but not in the NDVI time series. This seems related to the influences of aerosol contamination on NDVI. In conclusion, the VOD products provide unique global information about long-term vegetation changes over ecosystems with a mixture of grass and wood vegetation components, and appear to detect large-scale deforestation over tropical regions better than NDVI due to its greater penetration ability. Considering both products together provides a more robust structural characterization and assessment of long-term vegetation dynamics at the global scale. Nevertheless, this VOD product has its limitations. Several assumptions are made in the current UVA NASA model, including a constant single scattering albedo, canopy surface temperature equal to soil surface temperature, a quality of vegetation parameters for both horizontal and vertical polarizations, and a fixed surface roughness value. The influences of these assumptions on VOD retrieval accuracy and possible improvement of the current model required further focused investigations.